This is an introduction to the rotatable covered cavity kiln, called, sometimes spelled out RoCC, sometimes I'll say ROC kiln. And we're dealing with medium-sized production of pyrolytic biochar and thermal energy. Did I hit the right button? Nope, wrong way. Next, out of that. There we are. Topics to be covered in here, give you a little look ahead. Pyrolysis for profit and for other worthy objectives. Other worthy objectives certainly include scientific investigation and why you are here. There are certain things that you're trying to do, and I need to relate, and I want this all to relate to what your interests are. There is a gap in the middle size range of pyrolyzer technologies. I'm going to go through those, but I'm not trying to present an exhaustive list, and certainly not everything is included there. And we'll focus then on flame cap pyrolysis with two types, the open top, which is the best known, and then the covered cavity kilns. There are deficiencies in those earliest units with that, discuss those, and then deal with the major components of the ROC kilns and the issue that it's rotatable. Have some examples of sizes of the kilns and what you can expect. Business issues of patents, prices, opportunities, and I want this, hopefully in the questions, it will be how you define them. And then the RoCC kiln for climate intervention strategies and the fact that it is available for everywhere here. Try this. Whoops, there we go. I can scroll here. There are numerous profit centers for pyrolytic char making, okay? The pyrolytic devices technologies, they're in the center there, but they can produce charcoal products, thermal energy, biomass disposal, and other benefits. Now, we want to get combinations of these. If we're going to want to have lots of biochar production, it's very nice if we're also able to get some financial gain in terms of the thermal energy from it, or simply clearing away to avoid landfills or for fire protection. Look, and the other one, the other benefits, chemical derivatives, carbon offsets, and climate benefits, many of them are intangible, or maybe as society goes along, they will become part of the financial structure with it. This is simply a second view of the same type of slide with a few more words and details in it, and that will remain inside the presentation so that when people go back and look at it, they can study one or the other. Paralytic technologies of dry biomass, there's basically three types: the without oxygen, with limited oxygen, and with much oxygen. Without oxygen, the retorts, the laboratory scale, the test tubes and things like that, the atom retort, rotary kilns. With limited oxygen, we have gasifiers of various types with flaming pyrolysis. I call it glowing pyrolysis of TLUDs, where I've done most of my work on pyrolysis. And then the flame cap technology, which I refer to as cavity kilns of two types, the open top and the covered top. Open top with pit, trench, trough, pyramid, cone, kontiki, etc. And then with much oxygen, but we're still getting charcoal. If you have a forest fire, there is a lot of charcoal out there on the outsides of those trees and things. So there's, it does make charcoal that way, but it's not, certainly not a scarcity of oxygen. Cools down too fast. Kelpie Kilson has worked a lot with the conservation burn, and then we have the air curtain machines, industrial furnaces, and incinerators. We'll take a look at some of those as we go along here. I've classified the biochar production techniques by orders of magnitude. The IBI used similar way here, but they did not have each order of magnitude with its own separate name. So under a kilo, that's something in the laboratory. The micro, the small is from, the micro is from 1 to 10, small 10 to 100 kgs, MIDI 100 to a ton, and then we've got the medium, and then the large ones, and then the over 100 tons. And this is defined as the input of biomass in 10 hours of operation. Some of the devices become 24 hours a day operations, but most things, people go home at night and they're not trying to run these things at 3 o'clock in the morning. The objectives of each one of those, the laboratories are testing, etc. The micro is for the cooking. The small and the midi are for making biochar, from all that I can see. The medium, the objectives aren't really clear because we lack devices in that size. On the large size, it's for charcoal or for char, for chemical products, for power outputs with it, industrial, combined heat and power. Char is sort of secondary. It's there. It has an extra value. They're trying to make more char as it goes along. On the small size here, these are pictures of the TLUD stoves. The natural draft one is on the right, and on the left is the new, soon to be coming out fab stove from South Africa. This will be a whole separate presentation at some other time about what we can do for char making with the micro gasification systems. At the small size range and the midi, we have TLUD barrels, 55-gallon drums. Michael Schaefer in Thailand, Warm Heart Foundation, has had several hundred of the drums working at one time for the community. You get lots of things done that way if everything works out right. But the drum is about as big as it goes, with the exception of the work that's in Cambodia, which is some special equipment and special, much larger system. The midi size, including probably the retorts, the atom retort, without the oxygen present. The flame cap is also in the small and midi size. The pit kiln, the Kon-Tiki, the troughs, the trenches, the pyramids, they're all depressions or cavities where oxygen is not able to access the charcoal that is falling down into the bottom of those areas. These are the open cavity kilns. Closed or covered, not closed, but covered cavity kilns I've worked on, and there have probably only been about 8 of these ever made. There's a learning experience, but I've been working on it since 2014. The part of, okay, the medium size, I'm saying it's basically missing. If people are able to suggest things which will take in 1 ton to 10 tons in a 10-hour day, we need to see what they are. Basically, they tend to have fairly high prices, more sophisticated equipment, things like that. We need something which is affordable. It's a major gap, which I hope to have filled with the variations of the RoCC or rock kilns. The large size is on the far left, the industrial furnaces. These are large buildings. We're talking millions of dollars of equipment and the output and business arrangements. Rotary kilns are available, and also then the air curtain, which is available from several different types, but they don't produce that much biochar. Many of these things, they're trying to get other derivatives, they're trying to get the heat from it, and biochar is a nice extra if possible. On the evolution of the rock kiln, first of all, it is flame cap technology, also known as flame curtain. Is accomplished in cavities with closed bottoms. The classic flame cap occurs when there's an open top on it, the picture on the left, diagram on the left. And then we have the covered cavity kilns like the 4C kiln, clean, controlled, covered cavity kiln. I've really got the 4 Cs. With that, and the covered units have increased enclosure, but they're not rotatable. A list of various characteristics sharing them in between in there, but you can see the picture on the right which I have created, and it's available if anybody wants to copy it and put it into drawings and things. It's a representation trying to be somewhat on parallel with the diagram to the left, showing that at the bottom of the chamber is where the charcoal is accumulating. We have a layer in there where pyrolysis is occurring from the heat that is coming down onto the biomass from the combustion of the gases which are above it, above that biomass. And then because the covered unit is semi-enclosed, it is able to direct the gases emissions up the chimney, the heat up the chimney, and we hope to be able to utilize that heat better. It is and also be cleaner and have the ability to measure emissions and things which are inside. This is just another extra one. It's giving the same diagram side by side on a full-size screen so people can look at and read it more easily. There are deficiencies in the static or non-rotatable cavity kilns. Fuel in general, excuse me, in general, fuel input is gradual and it requires attention of the user. It is not something which is easily automated, certainly not without substantial cost. There is possible incomplete charring if some of the biomass fuel becomes buried. This is why the fuel input must be gradual, must be monitored. And this becomes a problem because you can end up with parts of actually raw fuel or torrefied fuel inside that static, non-movable cavity kiln. There's lots of pictures, people mixing it, trying to poke it with sticks and trying to get some kind of exposure for the biomass that might be getting buried. Lack of control of airflows. It does not readily scale up to much larger sizes. Nobody, I don't think, has proposed a 4-meter diameter Kontiki or other open-top cavity kiln. One exception, though, is Kelpie Wilson's the Turtle, which is a flippable half-cylinder. It's done, it's available, that type of thing to consider. And also it can become too hot for the operator to approach without equipment. As the units get larger, the radiant heat is immense and a limitation on the sizes that you can do with the static kiln, cavity kiln. And then extinguishing and extracting the hot charcoal becomes difficult as size increases. The solutions included in the rock kilns, we have tumbling of the biomass. This is when the kiln is rotated when needed. It is not a rotary kiln, which tends to, those types are rotating all the time, or they have internal parts which are rotating and augers and things. This kiln is only rotated on occasion. That's why it's rotatable rather than rotating. Let gravity do the work. It has one doorway or portal in it through which the air and fuel enter, and then the emissions and char come out through that one same opening. You'll see pictures in just a minute. And that opening has some different positions, which I also explain in a moment. It can have a movable grate or prongs that can come over this portal, and you could even have a doorway in special cases, and you can get the full 360-degree rotation without emptying everything out. Two forms of fuel loading, one by a horizontal shelf and the other from a vertical drop, to be explained also. And the unloading is downward onto a slide or into a container. We let gravity do the work. No handling, no shoveling in this until it's actually outside of the kiln. Then you can mechanize it, you can do other things with it. Chimneys, multiple, are separate from the kiln itself. The kiln rotates, the chimneys do not. The chimneys are on a detached hood, which is available. And the detachable hood is credited to Gary Gilmore, who's attending this webinar, I noticed, in Pennsylvania. he is listed as the co-inventor with me on the patent application. So we always should be thanking Gary for what he has done for us. Okay, and finally, we can use standardized industrial materials like corrugated steel pipe. Now we'll see some pictures here in a second. Steel pipe, we're going to scale from 2-foot diameters up to over 16-foot diameters, and they can be at appropriate lengths. This is additional benefits of this technology. It can be portable or stationary. Additional sensors, air control, directional controls of the emitted gases and heat, and operators are less exposed to the direct fire and the radiant heat. These are additional benefits. And the rotatable cover. This is fuel delivery is faster and more plentiful, and it does not matter that some of it gets buried inside because we have the ability to mix it. And also the fuel entry can be automated. We get more complete charring from this because of our ability to mix inside of the pyrolyzer. Better control of airflows. We are, I say, nearly continuous operations because there's a short break as we can take out most of, but still leave embers and ignition material inside the operation. And then also doing batch operations, so it's something that you can close down at the end of the day. You don't have to have expensive equipment that you really must run 24 hours a day. Low cost, we want low maintenance, we want low labor requirements, scale up to the larger sizes, and also to facilitate the extracting and extinguishing of the hot charcoal. We're going to deal now, we're dealing with the sizes of these units back there and the medium, and large sizes, 3 orders of magnitude into there. The different RoCC kilns span the sizes from midi to large. Mostly it's in the medium size range, which is the 1 to 10 tons. If it's 10 tons in a 10-hour period, you're putting in like half a cord of wood every hour into a device and is able to continue operating. And obviously, I mean, if you wanted to run it 20 hours or 24 hours, you get larger quantities. Okay. Here's some pictures now. At the midi size, which is like over 100 kg a day, these are mainly in 55 gallon or 200 liter barrels, the ones on the left and there. The pictures on the right hand side, there's 2 pictures here. That is a 3-foot diameter barrel, and that is with Manish Kumar in Odessa, India, and he is also on our attending our site today, so maybe he'll have some questions on it. All of us have problems with the lockdown, and so this has been a big setback for us. But I'd like to point out that the unit in the bottom 2 on the left side that is built was in Kenya, and it was built in 24 hours by a welding shop which works out on the street and brings its stuff in at night to lock it away. And this is not the high tech in order to get the things built. The upper left picture is literally an operational unit in my backyard in a residential area in central Illinois. It is not totally smokeless, but I have not had incidents with neighbors complaining or having the fire department show up or things like that. I'm not recommending that people in residential areas do it, but for development purposes, it's been pretty essential to be able to have something close to home. That was the midi size. Going to the medium size ones, these are 4 pictures from the 1 unit of this size that's been built. It's 4-foot diameter and 5-foot long. It's out in California. Thor Bailey, who is also attending this session, is the becoming the sort of, let's call it custodian or the caretaker of this unit that's out there. I live in Illinois. We built it in California. We test fired it at a conference that was out there in the very end of February, and we'll have some few more comments about this particular unit, but you'll notice the different parts and stuff. The large sizes, none have been built yet. The picture on the lower left is, I think it's a 12 or 10 or 12 foot diameter steel culvert, and they build them up to 18-foot diameters of very strong steel, something that we would like to be able to do. And this is reminiscent of what you would have with the air burner and the ROI carbonator, where you're feeding these units of this size with tractors, with grapple hooks and things. The picture on the right is with 1/16 scale models, and when they're this size, you have to be doing something with regard to getting the amount of fuel into them. And this is not something that I can do in my backyard or on my own budget. So I'm actually actively looking for people who are saying, let's go to a larger size. I give all my assistance with regard to making this happen, and that refers to any place in the world. Okay, the RoCC kilns have 4 major components and then numerous auxiliary components, which I'll illustrate in here. The cylindrical pyrolyzer with its portal, a rack onto which that pyrolyzer sits and it rotates with either an axle or with wheels, a frame for the hood of chimneys, and I'm noting that the rack and frame can actually be combined in some units. And then we have the hood and chimneys, which, as I pointed out, are separate from the pyrolyzer itself and take the emissions away. Auxiliary components, including the loading shelf and the discharge slide, and then other things. We'll have mechanization, instrumentation, handles, mixers, prongs, fingers, air control, insulation, heat extraction, and more things. The more I work with this, the more I find that little extra things come on, so, and are possible. Okay, get my cursor right here. All right. Of the 4 components, the cylindrical pyrolyzer, 55-gallon barrel on the left, an anhydrous ammonia tank is shown in the upper right. Current efforts, I have started the work to use half of that tank. It's a 4-foot diameter and 15-foot long, so I'm get 2 7-foot segments by cutting it in the middle, and then I just have to close off one end of it. Ready to go with this, where this is getting prices on it and things like that for doing things. Corrugated steel pipe, and the picture on the lower right shows you the prongs which are in there to keep that opening, keep that portal closed or partially closed, and those prongs rotate out of the way for when they're in use. So that's into the pyrolyzing cylinder. The rack for the pyrolyzer, variety of different types and shapes and things. The simple one that was built in Kenya is, the only thing I brought over to Kenya were these 4 caster wheels, and they were put together. The lower picture on the left is the one in my backyard, and these are cross members of shelving conduit, heavy, pretty good stuff there. The wheels come from the local hardware store. The barrel is a 55-gallon drum, which I modified and did it all myself. On the right-hand side, without a picture, is what I'm calling the I rack. It's built with I-beams and extended out the bases and top on it, and gives great strength. You can pick it up with a forklift and stuff. That's what's going into the unit that's being built with that anhydrous ammonia tank, half tank there. the frame that's going to hold up the hood. On the left is the simple one from, did I say Malawi? I'm in Kenya, okay? The X frame is shown there in the middle, and it holds it up, and the hood actually slides on the frame. It is not built and fixed, attached to that frame, because there's advantages to moving it. And then that I frame again, which would be for both holding up the cylinder and also for holding up the hood and chimney. Hood and chimneys, a flat one, the one in India with Manish is just a simple flat sheet of corrugated roofing metal that was torn off of one of their buildings during a cyclone that went through a few months earlier. And we build stuff out of scrap. We build stuff out of what's called obtainium. You find it, we use it. The two on the lower left are the unit in Kenya, and it slides back and forth. It slides over the top of the frame. And the ones on the right-hand side, this is out in the California unit, and here the hood slides inside of the frame and has its advantages. And the hose coming up to it is to illustrate that by using forced air, you can have an induction that's going to give you the draft by induction, and you can direct the heat that is coming out from this hood horizontally and then anywhere down and around and up and down into there. We want to be able to utilize that heat because it's considered to be of value to us. By the way, there is a video that will be out, that is out already as of today, that I'll give you an address on, that will be able to show you some things out of this unit there in California functioning. The unit in India, the picture here helps define that on the left-hand side, it is the front, because the hood and the loading shelf are on that side. It is not on that because it's left or right. It is defined by the position of the hood and the loading shelf. And therefore, on the rear or back side, we have the discharge slide or the collection box as it comes out. Now, imagine that this unit, not imagine, it does, it rotates, it turns, turning the handle on there, and the portal can be into any of basically 6 basic positions or movements. Again, the front is to the left, and left in this picture, depends on which side of the unit you're standing on, but the front is where the loading shelf would be at, and the back side is where the discharge takes place. The part A looks like a backward letter C. That is the normal operating position where the fuel goes in over that lower lip of the opening, and the gases and emissions come out through the just underneath the top of that opening that's there. The position B is if you rotate the kiln so that the portal is straight up. This is denying entrance of oxygen except for the minimum amount in it. This helps to control the fire, to tone it down. If you leave it in that way, and this can still be under the hood and operating this way, but this is where if you're trying to do a slower element on your pyrolysis, you do have to, with sensors or watching it so that it is possible to totally extinguish the flame in there because you're not getting any oxygen, and it will not exactly snuff out easily, but it's there, it will end. The one on the right, which looks like the normal letter C, this is the back side, and it can be then in that particular position without the hood over, how you can actually bulk load this cylinder, the pyrolyzer, without obstructions of the hood and or with other mechanisms on it. The slide for sliding in the fuel is on the left, is on the front side, and the opening is to the right side. When you turn it straight down, D, and it's conveniently D for dump or down, This is how you're removing the char, and it just falls out very nicely into whatever container or sliding slope or something that you have arranged for it. E represents the rocking of the cylinder back and forth slowly or with quick movements if you'd like. More than 180 degrees are possible in there without spilling the char out of the unit. And then you can do a complete rotation, a full rotation on it, mixing extensively, like if you have the prongs in there. And then this would be only in conditional situations that it can be done that way. Okay, all these things have come out of our experience with the kiln. This is just to point out the wide variety of biomass types and shapes that we could use into there. I put down that sawdust is problematic. It would cake up and stuff like that. It is not something that I'm particularly fond of doing, as are also mulch and wood chips. They could tend to accumulate and bury each other and insulate and keep the heat from getting to there. However, for the easy ones, things of stems and reeds, brush and small branches, anything that you can push in through that portal doorway manually or with an apparatus that's taking it in. Arm-sized branches will pyrolyze very nicely. I've noticed that a 4-inch, a 4x4 piece of timber will be completely pyrolyzed in about an hour and a half inside of the kilns, which are in those midi range, the smaller size stuff. Cordwood, slab wood. This is excellent material that comes off of sawmills. It is monstrous supplies of this, long, can fit through that portal. We simply make the rock kiln not 5 feet long, but we make it 8 feet, we make it 12 feet. If you want to put it in, you could have a 20-foot long thing if you have 18-foot lengths of something that you wanted to put in, and they would just feed them in if you have that feeding into there. And then we rotate it inside. Whole trunks, you'll need time for pyrolysis there, maybe even handling root balls with dirt on it. Makes no difference in this pyrolyzer. The dirt will be mixed in with the char. If you're trying to make biochar, it's supposed to go to roots, into the soil anyway. So the ability to handle so many different forms of biomass can mean substantial savings on current pre-processing of biomass that needs to be disposed. Yes, people are grinding and chipping things, in part because that's how they can handle it these days. But if you can avoid the costs of grinding and chipping and take this stuff directly in, you'll be able to feed the RoCC kiln and get the results that you want. I made a table of the sizes of the kilns, and I'm revising it, but I wanted to leave it available as a sort of a reference document into there. We're not going to try to read the details of this thing here, but it is in the manual, which is on the internet, but noting that it's being superseded even as we speak. I have extracted from that something more selective, selected sizes of RoCC char makers. Column B in the MIDI scale, that would be the barrel. Columns D and E in the medium size are the utilities of some sizes into there, 4-foot diameter, 6-foot, could be a little bit larger than that. The large scale units would be 6-foot, 8-foot, 12-foot diameters that we could have. Oh, I didn't mention on the other slide, a large size for a large scale container could be a railway tank car. Now, this is getting to be pretty serious with regard to the amount of biomass that you need in order to fill this in. But those railway tank cars are being replaced throughout North America because of safety requirements. They're going to double walled and other types of things, and they are literally available at scrap prices. I'm hoping that somebody either listening here or will be mentioning to somebody who knows somebody who says, I'm willing to have a go with something we'll build up to those large sizes. Those are 10-foot diameter by like 50 feet long, but we can also do the larger diameters and keep them shorter. It is what we need and how we want to do this. The volumes are given there. The fuel input is in kilograms per hour, and then putting in some more stuff like that. You'll notice that in column G, the large scale, this is a, no, I'm sorry, column E, this is the 4-foot and 8-foot length is like that anhydrous ammonia half tank that I was looking at doing. And it would take about 5 tons of biomass input per workday. Again, it varies from type to type, thicknesses and stuff like that. Char output, I do my calculations based on about a 20% char yield. We are, with flaming activity in the area, we are not, we do not do 350-degree pyrolysis. I mean, it is not our nature to do that in these covered cavity kilns. So the thermal output is calculated down there. I'd like to point out that all these numbers are extrapolations off of what we've done with a barrel. And they are not, therefore, totally accurate. We have to show it to be done. I'm reading in column A, row 3, extrapolation in there. Based on volume, there is less if based on the horizontal area of the flame cap pyrolysis. But when I'm looking at the numbers in here, how much energy we could get out of it, if the numbers are wrong for column E as to how we can get 2.8 million BTUs per hour coming out of this char maker, those numbers could be very appropriate for column G or for column I or for other sizes in there. We are able to get 1 million BTUs per hour. We are, or we can go to 5 million BTUs per hour. And it's what we're after. Are we after heat? Are we after char? We're after both. What's the rush? We're just trying to get through all of the, get through that biomass because it's a safety hazard. Okay, that's a different one of those 4 reasons why we do pyrolysis. So none of these are specified. They will all be or predetermined. All of them will be arranged as we relate to the particular needs of the people who want to do pyrolysis, who have the biomass, etc. There we go. I didn't get very far on a hypothetical scenario for a utility-size rock kiln, but abundant biomass of slabs or urban wood waste. Michael Schaefer has interests in Thailand on how to do it of the straw and field stubble that they have so that they don't have the air pollution. Michael spoke 2 weeks ago to this group, gave an excellent presentation about the issues there and the need for pyrolysis to be able to handle in fairly big volumes. That is a special topic of interest. I'm working on it with Michael. We have a design for a unit to be built. Of course, the coronavirus is causing shutdowns for everybody everywhere. So if that is of interest to some people, please let me know. Please be in touch with me. The need for heat and hot water, an apartment complex, a school, a small industry. What size of char maker do you want to have? We want the heat, and we don't want to burn it all the way to ash. We get the valuable char, and we get the carbon sequestration value of this. We are able to replace fossil fuels, avoiding the carbon tax that should be on fossil fuel, and maybe we can even get some of that money paid for the biochar that is produced. Biochar for agriculture is increasing value as we move along. Carbon sequestration increasing importance, and I think that we should not be thinking in terms of 1 year, 3 year scenarios, but 5 years down the line, 10 years down the line, the situation is going to be so much different and so drastic that this is going to be a major concern for us and the carbon sequestration value. The RoCC kiln invention has patent pending status. We expect coverage until the year 2040. This protects my interest, but it also protects your interest because I'm hoping you'll become involved and interested in this in some ways. This is the discussion of the investors. Oh, they've got to have patent protection or something, intellectual property rights. We've got it, and being processed through all at the international level. But only when there is financial gain based off of this pyrolyzer, then some small share should come to the inventor. In other words, item 3, there are no upfront fees to become involved with the RoCC kilns. You get my advice and assistance basically for free. I can't travel around the world for you, but for free. But I'm helping you with all the different things about it. And you can make a unit and do it. This is for your own personal use. That's fine. But when somebody is making money off of the RoCC technology, then I will be talking with them and something reasonable. That's the way we can help finance and move things all forward. And therefore, with regard to all of you, all options are open for business arrangements. If you are interested in making devices, selling devices, using them to make the char that you would do in the quantities that you need for your purposes, you want them for energy, you want them for climate benefits or more, all of those things are available and open. I don't make a big deal out of this, but I'm 76 years old. I'm in excellent health. I expect to be around for the 20 years of the patent. However, I'm not doing things on my own. I am looking for people who wish to be involved with this, want to be involved with it. You, in your geographic area, in your field of activities, could benefit from the RoCC kiln. There's going to be some grants and things done. I'd like to be included in them, and I bring the kiln along with, the technology for it, so we can make the bigger ones. The Forestry Service should have something. The U.S. Department of Agriculture interested in this. Well, how can we make charcoal in that median gap of where we don't have the pyrolyzers like that? And of course, then we have to look at what's the price of these units. Okay, next slide here. The barrel size unit. About 3 foot diameter, 4 foot long, something like that. Do it yourself for your own. It is essentially free. Use your own scrap, find your stuff, find your materials. I will advise you. This is why I'm sharing everything so freely out with the on my website and via this webinar, and also with the with the other videos and things which are available. If you're going to purchase a ready-made, then somebody is out there supplying this. I'm willing to work with somebody who wants to be a supplier of the particular types of materials and devices. Make an arrangement with them, an offer they can't refuse. It's something that'll be good. I would point out that for the barrel size unit, a less expensive variation, not to be disclosed here yet, should be available a little over a month from now. And I'll have that announced. Something I think you'll find it interesting. This is on the barrel size. Utility size, sort of the 3 foot to 5 foot diameters, up to 10 feet long. The costs are between $5,000 and $10,000. Somebody's going to have to make it. This is buy these tanks, buy the equipment. There's welding. There's work with that. I will assist you to help you locate a supplier or work with you on it. We have efforts to have the ability to make the units here in central Illinois, also with Thor for prospects for making units out on the West Coast, out in the Northern California area, and wherever else there might be the cases. Certainly overseas, I'm looking for arrangements with for people in different countries, and I'm not going to be there. If you're waiting for me, you're going to wait a long time. And I want to help you, and I need to work with people. And special arrangements for making units with features not previously included for heat and heat capture and use. People who are in the business of furnaces and heating buildings and stuff like that, this unit is providing a source of heat. Everything else that they sell, the boiler, the tubing, the pumps, and all that type of stuff, that's not my business. That is something that they do, and they do it well. And I am looking at helping them to have an alternative source of abundant heat, and in the process, we'll be able to get the char from it and the energy value, but also the climate value. So for bulk size units, these bigger ones, just get in touch with me. I'm certainly interested in talking with possible joint research efforts, business efforts, etc. Almost finished into here. Let me check quickly this. Okay, got to be done fast. For climate intervention strategies, there's this 4 ways of making values into there: abundant biomass, many benefits, decentralized, because the biomass is decentralized. Decentralized biochar production is a highly appropriate, accessible, and reasonably priced major climate tool for carbon dioxide removal. I make that as a blanket statement, looking forward to somebody challenging me to say, hey, let's make that happen. I want to do that. Major accomplishments come from many, many small individual efforts, each making small contributions, and we can end up with gigatons of carbon sequestration coming through from that. And this is all becoming available. Notice the world needs things, and for energy, agriculture, biomass removal, sequestration. It is possible now with these medium-sized appropriate technologies. The accessible, the technology is willingly shared. If you're interested in this, I will get into the details, into the weeds of how to make something happen. Opportunities of ownership and rewards for the potentially profitable activities or for your research activities and things like that in your local areas and regional areas. I will try to coordinate the exchange of the information so something that's developed up in New Zealand becomes available to people who are trying to do it in Alaska versus people who are in Europe or Africa, etc. And so I say, why not? Concluding in here, if or when there is another technology that can fill the gap for medium-sized pyrolysis units, as well as or better than the rock kiln, we should all endorse it, and I will also. But while you're seeking or waiting, the rock kiln technology is available for your consideration. I'm making it available, and then it will become something for you people to do. Summary is, it fills the gap, it makes the char, many different places and uses, possible scales, very large sizes, resources at the, I'll come back to this screen so you can see it afterwards here and copy it down. Woodgas.com is my website for the wood gas pyrolytics company that I have, that I've set up for it. And the resources page, there's many different things, including the manual, and also the video is available at that place. It's a 4-minute video. I thank Rocky Thompson, who is also on this presentation, on this webinar. He's helped greatly in preparing up a copy of this YouTube that'll show you in operation, doing things like that. It's an introductory piece. Direct access to me for whatever you're looking for. There's my email address, which is widely distributed. Demonstrations, I hope that they'll be possible out in California with Thor, and in India with Manish, and in Pennsylvania with Gary, and in Illinois with me, and we'll find other places that are going along with it. And final one is my contact information. Again, if you get to woodgas.com, which is the old website of the Biomass Energy Foundation from Tom Reed, which I have sort of inherited on it. So we can work on with that there. And I would point out that I'm not going to show them, but there's 4 extra slides to help visualize the volume and the energy associated with 1 ton of biomass, 5 tons of biomass. Just quick things like that. If people wanted to look at that, that's just attached on at the end of it. So there's the slide that I'll finish with there. Thank you very much. I'm sorry that it's gobbled up most of the time for any questions. I can stick around, but I don't know about you. Sorry, it's hope you found it interesting. Thank you.
Thank you very much, Paul. Really nice presentation. Interesting new technology, and I'm sure there are some questions from the audience. We still have as much time as we want to take, so no worries there. So you got already a couple of questions in the chat during the presentation. So Brian was asking, what sort of hot process applications are you finding for the heat of the process?
Okay. Question is phrased wrong. It's not what I am planning. It is what we are planning, Brian and all the others. Okay. An American house in the wintertime needs something like 40 to 50 thousand BTUs, and one of these rock kilns is going to produce a million of them. So I mean, you can heat an apartment complex, you can heat schools and things like that, industry things. We are not. I am not involved with trying to turn the heat into electrical power. Certainly, situations exist that can be done. I need people who have that expertise and that they want to do it, and we'll work together and make this something extremely successful. So heat wherever you want it to be. Okay, and means for making biochar, but also for just the heat value.
Next question also from Brian was about how much water you need for quenching of fire safety of the kiln. I guess you have to choose any size of the kiln you want to answer the question for.
Yeah, okay. What I do with my work, because I want to know the weight of the biomass going in and the weight of the char coming out, is I don't quench it at all. I mean, I get down into my barrel size unit and I bear the heat and I put it into buckets and I've got a lid on it. I can weigh it so that I don't have water in it. So that's one way of doing it. You just quench it with containers which are made to seal up on it. One of the techniques is that it would be actually buried. The unit I'm talking about with Michael Schaefer in Thailand, as they're going through the fields, they make it up, and once the cylinder is about half full, because you don't take it beyond the halfway mark because of the shape of the portal, you will then you pull it over to a spot, you'd have a trench, you run it and you tip it, it dumps down in, you throw the dirt that was taken out of the trench over the top of it, pack it down, and you're going to get your char collected into there. Again, you will find that whatever it costs to make the cylinder itself and to making the char, there are far greater costs when you want to put on automated fuel feeding, you want to have water extinguishing, you want to have the heat used for boilers and things like that. Those, you can make hundreds of $1,000 units in there, and it's still using just the basic core RoCC kiln to give you the heat. So that's the answer to many of the questions that are probably coming. And again, it's what you people want to do, as I'm looking for working with people.
The next question is from Ebbing Osinger about the carbon balance of your process. If you know how about the emissions in the flue gases from this kiln.
Okay, as I said, it is not perfectly clean, but in terms of comparing it with automobile development, we are just past the Stanley steamer and haven't even gotten up to Henry Ford yet for making automobiles. So the improvements will be coming as we figure out how to bring all the emissions in. However, it is my experience quite quite clean. I want to have sensors put into it. It'll be built into it. There is an expression about the perfect being the enemy of the good. I'm not trying to present it as it's got all of the solutions down perfectly on it. And someone who is very interested in emissions and emissions testing, that's again, we need those facilities and those types of people to participate in with projects. Maybe we get groups together that can help with that.
Thank you. Then you.
Oh, I will say on emissions, it is, I believe, I'm quite sure, notably cleaner than what is able to be done with a flame cap with an open top, just because of crosswinds and other things like that.
The next question was about is the intent to stay with non-forced air addition as the design is scaled up? From Hugh McLaughlin.
I'm sorry, say it again, please.
Is the intent to stay with non-forced air addition as the design is scaled up? So for the big units, is there still?
Oh, yes. It is possible to have forced air going into it. The end plates of the cylinder rotate, but they're not the circumference. You know, they're on the end. We can access in. We're able to put things in. If you want to have a more sophisticated pyrolysis control with probes and sensors and things into it, you're able to. You don't have to have the open door type of flame cap. You have to have an access to be able to put fuel in, but you can add your air in through separate ways. You run it as your batch. So because these units are where the char is accumulated at the bottom, we are not trying to put any forced air in down where the charcoal is accumulating, because that basically becomes a forge and it can shorten the life of our unit. The air burner units have such high temperatures that they have to be all lined with special ceramic brick and things like that, and we're not that hot. We're down there, it's actually cooling off down below into there, except for when you mix it up or trying to get stuff in. The beauty of the flame cap.
Do you know what kind of temperature level you get for the biochar itself, more or less?
I'm thinking we're in the 550 to 600 centigrade range, and you can stick in probes, and that again, if somebody is in the scientific community or university community, getting better measurements on this would be fine. I'm hoping somebody's listening who either is or will have some student that's going to do some research topics, and it'll be first time done. I don't have all the answers, but it gives good char. I've had Hugh McLaughlin has checked my char. It is a moderate char. I'm not claiming it's exceptional, but at the same time, I'm sending him stuff of first, second, third times I've ever run a unit and that type of thing. I think we can try to get it. And also, when you have a reasonable char, there are processes to further process that char at higher temperatures and to get it to the designer char characteristics that somebody might want.
So another question from George Chaffee. No idea if you pronounce it like that. Can you add a spark arrestor so that you could process forest flash year-round? He's thinking about putting it on a trailer for forest fire prevention in Western US.
A spark suppressor. What we do well is get these emissions and everything to go up through under that hood and into the chimneys. In those chimneys, you can put anything that you would like. Spark suppressors, you can have extinguishers that will trigger off if something happens. You can do any number of different things. Interested in this unit for the biomass reduction problems. I had a visit out to Paradise and saw the site, not, after they're cleaning up and everything on it. and the fires that went through on there. That's such a big topic, and it could be that these units are built up to an 8-foot diameter cylinder is highway worthy. I mean, you don't have to have a wide load permit, and an 8-foot diameter will be a substantial, will take in substantial amounts. Certainly 10-foot, 15, a 20-foot long unit made out of corrugated steel pipe, the culvert type of stuff with heavy gauge. It'll last a long time. I've got people that can build that. I just don't have someone who's going to take the first unit. I can't build a unit myself and then say, hey, I've got something, would somebody be interested? I've got to participate with others to make it happen. But yes, for these fire issues, I think we've got some solutions.
And then there was a follow-up question on the carbon balance from your process. What do you think? What percentage of carbon is staying in the char? So, what's your carbon balance of your kiln?
Yes. Okay. We have some measurements that have been done, and we know that these chars are about 80% fixed carbon, or the resident carbon into there. There's some volatile matter left, a little bit on it, and some ash that's in that the other 20% by weight. But they've good results onto that side of things. The unit is under the control of the operator, and when we automate it, the unit that's being built now is going to have mechanized motor on it for turning it and things like that, and then it can have a controller unit on, and so we can set it up for the right temperatures and stuff that we want. But I'm predicting that this is going to be quite reasonable biochar that people will want to have and can have in quantities. So, and as I said, if we have hundreds of these units out there doing it, the calculations are eventually thousands. They become gigatons of CO2 equivalent, which has been effectively removed from the atmosphere, first by the plants, and then made into a fixed form of biochar using kilns, my kiln or other kilns.
Let me check. Yeah, there was one more question from Robert Lemmert. Have you thought about making the frame telescopic so you can transport the unit on the truck, so you lower the center of gravity to transport it easier on the truck, I guess? Okay.
The unit itself, if it's 2 feet off the clearance off of the bottom and an 8-foot diameter, it's a 10-foot height, and you have the chimneys on it, I would say instead of telescoping, I think they would either be detachable or they would fold down like major stacks do on ships that go under bridges. Okay, there's a hinge on it, and the stack gets bent down for a while, and they get through, and then they put it back up again.
Okay, some of the questions were already answered by Manish Kumar in the chat. So any more questions? Please write it down now. We'll wait a little bit more.
I'm not planning on showing the video here at the webinar, partly because of bandwidth and sending it accessible to everybody at the website. But I do recommend that people would go and look at it. Just a little over 4 minutes. And again, I thank Rocky Thompson for his great assistance with that. And he and I are planning to do some other videos that address more detailed issues of the about the equipment, and not just the introductory one that we've done.
Brian has a question. Brian, just ask if you want to.
Hello, can you hear me?
Yes.
Yes.
Yes, I was just Would you advocate building bigger kilns or having more smaller kilns? It's basically scaling up versus paralleling up and having a bit of redundancy.
Yes. Okay. I believe that an institution or a place that needs, say, a lot of heat is usually better off if it has 2 or 3 units, and therefore when it's only springtime or fall, they're only operating with 1, and then they're at the height of the winter, they've got 3 of them going, and this lets you do maintenance on them and things like that, as opposed to doing 1 which is gigantic, and then most of the time you're running it at 2/3 capacity, and which is not necessarily a optimal for the result of emissions and the biochar, etc. So I agree with you that yes, many small ones.
Yes, thank you. Thank you very much for your presentation.
Where are you from, Brian?
I'm from Northern Ireland originally, but I'm living in the millionaire's playground of Slough, just in the Thames Valley of England at the moment.
Yeah.
It's doing most of my experimenting at an allotment in Denham. But no, it's just I tend to sort of gravitate to T-luds, and I've got the variation. I've got the RBOP burner, so it's I look forward to sort of hearing more of your talks.
I hope that we can get a unit into Ireland there. As most people know, I did 18, 19 years of work with T-lud stoves. I'm still working involved with them, and so I did not come from a background of combustion and pyrolysis and char making and things like that. The T-lud stove made the char, and that's how I got into it. But as I've been to the conferences for biochar, et cetera, the constant comment is we have to make something which is bigger quantities without being really expensive. And I worked on the 4C kiln, and I have to say after 5 years of having that and stuff, I realized it didn't work. It didn't work well enough to really scale up. And so then I went and I spent $4,500 on a unit that didn't work. That's this whole separate story. And then I said, okay, I'm going with the Rotatable, and it works. And I've got several of them out there and functional. So it's not a question of does it work? It's a question of we need to put it into practice.
Yeah.
There's one more. There's one more question that follows up on that, I think. So George is asking if there are any emission monitoring requirements for units like this in the US. Are you allowed to use them?
In my backyard, they don't even know I'm using it. I mean, and they're not going to be out. They don't do that. And my biggest thing is if you're not supposed to have open fires. I'm very enclosed. I mean, it's quite enclosed with it. The emissions on it, certainly when you get big enough, I mean, if you go over 1 million BTUs in energy in thermal output, as you are pushing the limit as to, inviting and it needs to be tested, needs to be checked. And there are many ways of scrubbing and or not. I don't do scrubbing, but of getting a cleaner burn, a pilot light to make sure that it never will lose the fire of burning with the hot gases. Using taller chimneys or longer chimneys. One of the things that we want to do is to take this waste heat and use it for drying the fuel, which is going to be coming in the next hour or the next day or the next week into the unit. And it's simply, we've got the heat. We'll have more than enough heat for doing the drying, but you have to have a room for putting the drying. So all of them are questions which have to be looked at, and I am certainly not trying to skirt away from fulfilling obligations with regard to recommendations, or, and requirements for low emissions. But at this particular scale, this is really the grassroots moments for this technology. And I thank the Christian and the Green Carbon webinar series for giving me this opportunity to express it, to see it, to get some exposure on it.
I think that's a beautiful ending. We are quite far in time, so thank you again, Paul. Really interesting, and I'm sure you will answer any more interesting questions if someone wants to write you.
Yes, please
as
do.
you said before. And